In this lecture, I'll present the rules for permutations and combinations and then give a little review on factorials. Permutations and combinations are the total number of possibilities given certain conditions. They're used often to find the size of a sample space, especially if it's based on the arrangement of different items. So by definition, a combination is a group of selected objects that without regard to order. And that's hard when you try to say without regard to order. What does that really mean? It means that if I reorder it, it's the same combination. It's the same group. Say I have a committee of Billy, Bobby, and Susie. If I write the committee members as Billy, Bobby, Susie, or Susie, Billy, Bobby, or write them in any order, it is still the same committee. It doesn't matter what order I write the elements in, that does not change the group. Permutation refers to a group of selected objects in which order really counts. And the example I'm giving here is that if I have a post office box 425, that is not the same as a post office box 254. When I change the order of those numbers, it changes to a new item. So that's the difference between combination and permutation. There are several notations that are used just to state permutations and combinations. The equations are all the same. So we're going to let n, following Mendenhall, be the total number of objects that are available. Say you want to choose letters and digits for a license plate. The total number of letters available is 26. The total number of digits available is 10. If zeros allowed, otherwise it'd be 9. Okay. N is the total number of objects available. Little n represents the number of objects that you're going to select. Say the license plate has 3 letters, then little n equals 3, while big N equals 26. If you're going to select all of the objects, then little n is equal to big N. When you go to write the just the name of the permutation or the combination, you can see the different ways that it's written. I generally write things like this, but this is very common for combinations also. Okay, the equations, though, no matter how much you write the name of it, are the same. For permutations, it is the total number of objects factorial divided by the total number minus the group to be selected factorial. Now look at the expression for combinations. It starts off just the same as for permutation, but then is divided by another n factorial, little n factorial. And why is that? Because you expect fewer combinations than permutations. So, for example, if you had a combination of, say, 2 letters, well, 3 letters, or let's do 2 letters, 1, 2, and 2, 1. The 2 letters, 2 numbers. Okay, 1, 2, and 2, 1. All right, in combinations, these are the same combinations. This would be, the number of combinations would be 1, but the number of permutations would be 2, because this reordering doesn't change it for a combination, but it does for a permutation. So you see here for the combination, you're dividing by n factorial. That reduces the overall number. Again, unfortunately, in this class, we won't derive these. We're simply given these formulas and using them. And here's an example on their use. Let's say you have a box and there's 8 books in the box and you're going to put 5 on a shelf. Now if the order of the books on the shelf makes a difference, it matters whether you put I don't know, the atlas first and then you put the dictionary versus putting the dictionary first and then the atlas. If it matters, then you have a permutation. And the equation for the permutation, which is the number of different combinations you can make out of 8 books, taking 5 at a time, the total number factorial in the numerator divided by that difference factorial in the denominator. There's 6,722 permutations. let's look at the number of combinations. Say it doesn't matter. You're going to call it the same thing no matter which books you put first and second and third, as long as they are the same books. Then that's combinations. Same calculation up to this point. Divide by another 5 factorial, and there's only 56. Sometimes these kind of problems can be done using a diagram, using one of these decision trees. Of course, you can only do it if it's small enough. And here's one for pizzas: thin crust, thick crust, and different toppings. So you can start here, separate it out into this either thin crust or thick crust. Then each one has these different combinations: mushrooms, cheese, onions, or pepperonis. And then if you count the number in this column, that is the total number. All right, this is the number of possibilities. Here it's 8. Okay, we can use the formulas also. We're talking about and here. There's some kind of crust and some topping, and in probability is a multiplication. So you have a combination, okay, of, I use the notation that Mendenhall likes. Okay, two possibilities taken one at a time. What would that look like? 2 possibilities is 2 factorial. 2 minus 1 factorial here times another 1 factorial, which is just 1. This is sort of a theoretical example. Now let's look at the 4 toppings. 4 factorial taken one at a time, because you're only getting 1 on this pizza. 4 minus 1 factorial, and then divided by another 1 factorial, which really doesn't matter. So in this case, permutations and combinations give the same number, and we end up with the 8. Okay. So now I'm going to do a short review of factorial. I know this is at the end of 107, and some people might not remember it. Okay, what does factorial mean? This exclamation after number means count down and multiply as you go. And you count down, of course, to 1. If you count to 0, that would be a little too easy. Okay, so all you do is first number, put the exclamation, means 6 times 5 times 4 times 3 times 2 times 1. There is a button on your calculator for factorial. There's a general rule for factorial. If you notice, look at this. What is all this stuff? That's 5 factorial. So 6 factorial can be written as 6 times 5 factorial. All right. And you can, of course, here's the general rule, which is expanded out. But this is very useful in simplifying calculations. This kind of a breakdown right here. Also, it gives the rather surprising result that 0 factorial equals 1. So if you have something like 3 over 0 factorial, okay, that's not undefined. 3 over 0 is undefined, but 3 over 0 factorial is not undefined, because 0 factorial is 1, and that can be proved by using this particular rule. Now let's look at the benefit of that abbreviation. If I can write, let me get the pen here, I can break down a factorial, and where I stop, it's going to be factorial from there on, like 6 times 5, well, that's not a 5, times 4 times 3 times 2 times 1. This is 4 factorial. Why would I stop there? Because, just a second, let me adjust the screen. Look at it this way. If I have 6 factorial over 4 factorial, I could write this out. 6 times 5 times 4, 3, 2, and 1. 4 factorial is 4, 3, 2, 1. Then I can go through here and just cancel. Well, okay, to get 6 times 5. All right. It's not necessary to do this. You can abbreviate. So I could have also written this as 6 times 5 times 4 factorial, and cancel this as one group and get the same answer, and it's correct. Now, of course, for a problem this small, it really wouldn't matter if you counted down and then canceled versus just canceling the factorials. But if you have something, for example, like this, you don't want to count this down to 1 and then do a lot of crossing off. Instead, you would just count down to where you have the numerator and the denominator factorial the same, cancel those, and then that's your answer. Again, calculators have buttons for factorials, but it's good to know what the answer sort of should be, and it's also good to simplify a problem first before going to the calculator.